Welcome to Lesson 15, Solving Non-Homogeneous Ordinary Differential Equations by the Variation of Parameters method. So here's the problem. We want to solve this non-homogeneous ordinary differential equation that we just looked at, and somehow we know the general solution to the corresponding homogeneous ordinary differential equation. Instead of g of x on the right-hand side, 0 on the right-hand side. Let's suppose that we do have at hand the general solution to this differential equation. That raises an interesting problem. We haven't solved, in general, differential equations like this unless we had constant coefficients. But for the time being, we'll assume that somehow, maybe by very good guessing, we have the general solution to this. We're able to find two linearly independent solutions to this homogeneous equation, and because of linearity, then C1 times the first solution plus C2 times the second solution would be a general solution, where C1 and C2 would be arbitrary constants. So in any case, under the condition that we've already solved somehow this homogeneous problem, how do we solve this non-homogeneous problem? That's the question we have to answer. And here's the technique. First, solve L of y equals 0, the homogeneous ordinary differential equation. Let's suppose that the solution, the general solution, is y equals c1 f sub 1 of x plus c sub 2 f sub 2 of x. Then let's consider the non-homogeneous ordinary differential equation L of y equals g of x. What we'll do is look for a solution of this form and compare it to what we have up here. Here we have y equals c sub 1 of x f sub 1 of x, where c sub 1 is a function, plus c sub 2 of x f sub 2 of x. So here we have constants in front of the f's. Here we have functions in front of the f's. This gives us a lot of latitude because there are many more functions than constants. So we can require that c1 prime of x f1 of x plus c sub 2 prime of x f sub 2 of x equals 0. We can get away with this, as we'll see later. We'll plug this solution up here into L of y equals g of x, use this condition, and we find that we can solve for c sub 1 prime of x and c sub 2 prime of x. Once we get those, we come back here and we notice that we need c1 and c sub 2. So we integrate c sub 1 prime and c sub 2 prime to find c sub 1 and c sub 2. Once we have those, we can find this solution up here to this non-homogeneous ordinary differential equation. So how can we solve this non-homogeneous equation using variation of parameters? Let's suppose the general solution to this differential equation equals 0. This homogeneous ordinary differential equation is y equals a constant c1 times f1 of x plus c2 times f2 of x. Then, for the non-homogeneous ordinary differential equation, let's look for a solution of the form c1 of x f1 of x plus c2 of x f2 of x. In other words, replace these arbitrary constants up here with functions of x. That gives us much more latitude. We can put some extra conditions on those functions c1 of x and c2 of x. That will help us to solve the equation. So let's see. If we differentiate this using the product rule, we get that y prime is c1 prime of x times f1 of x plus c2 prime of x times f2 of x plus c1 of x f1 prime of x plus c2 of x f1 prime of x. Let's demand, as an extra condition, that C1 prime F1 plus C2 prime F2 of x equals 0 for all x. In that case, if we go back up here, this expression for y prime simplifies just C1 F1 prime plus C2 F2 prime. And that's because these two terms we're requiring the sum to equal 0, and so y prime is just these two terms. So let's remember, if we require C1 prime F1 plus C2 prime F2 to equal 0, then y prime turns out to be C1 F1 prime plus C2 F2 prime. Let's differentiate this again to find y double prime. Okay, in that case, use the product rule on this first term and use the product rule on the second term. So we get y double prime is C1 prime F1 prime plus C2 prime F2 prime plus C1 F1 double prime plus C2 F2 double prime. So then if we substitute what y prime, and y double prime are into the left-hand side of the differential equation, what we get is the following. For this second derivative, we get this stuff. C1 prime F1 prime plus C2 prime F2 prime plus C1 F1 double prime plus C2 F2 double prime. Then, excuse me, we have p of x times the first derivative, but the first derivative is this. So that gives us plus p of x times the quantity C1 F1 prime plus C2 F2 prime. Then to that we're adding q of x times y. So that's q of x times the quantity C1 F1 plus C2 F2. Now let's rearrange these terms to the following. Let's have C1 prime F1 prime plus C2 prime F2 prime plus C1 prime of this quantity, F1 double prime plus P of x F1 prime plus Q of x F1, plus another term here, C2 of x times F2 double prime plus P of x F2 prime plus Q of x F2. Now let's remember that F1 and F2 are solutions to the homogeneous ordinary differential equation. So this stuff inside the braces equals 0 for all x. Down here, this stuff in braces also equals 0 for all x. So what we have is that this differential expression up here just equals C1 prime F1 prime plus C2 prime F2 prime. Well, we want this, remember, to equal g of x. So that's going to force us to have this first line of stuff, C1 prime F1 prime plus C2 prime F2 prime equal to g of x. So we just found out that this differential expression, under the assumptions we've made so far, is equal to C1 prime F1 prime plus C2 prime F2 prime, and this has to equal g of x. So that gives us two conditions on C1 and C2. The first condition involved C1 prime F1 plus C2 prime F2 equaled 0. And then the second one was C1 prime F1 prime plus C2 prime F2 prime equals the non-homogeneous term on the right-hand side, g of x. So we solve these two equations for C1 prime and C2 prime. We know what F1 and F2 are because those were solutions to the homogeneous problem. So, and we know what g is from our differential equation up here. And so the only unknowns are C1 prime and C2 prime. So we can use algebra to solve these simultaneous equations for C1 prime and C2 prime, just like you learned maybe in junior high school. Then you can use what you learned in college to integrate to find C1 and C2. These are just the antiderivatives of C1 prime and C2 prime. Then once you have found C1 and C2, you can form a particular solution to the non-homogeneous problem. C1 prime of x, F1 prime, F1 of x. Let me say that again. The particular solution is C1 of x, F1 of x, plus C2 of x, F2 of x. So that's one particular solution. Then, if you include the solution to the homogeneous problem, you'll get the general solution to the non-homogeneous problem. So let's consider this problem. Solve the second derivative of y minus the first derivative of y minus 6y equals sine 2x. Okay, we'll start by looking at the corresponding homogeneous differential equation, and the characteristic equation is going to be r squared minus r minus 6 equals 0, and that factors into r minus 3 times r plus 2. So we get the complementary function y sub c is c1 e to the 3x plus c2 e to the minus 2x. So this is the solution to y double prime minus y prime minus 6y equals 0. So now for this non-homogeneous problem with sine of 2x on the right-hand side, we'll look for a particular solution y sub p of x, which is c1 of x e to the 3x plus c2 of x e to the minus 2x. And so the first equation, if we think of f1 and f2 as being e to the 3x and e to the minus 2x, we have c1 prime times f1 plus c2 prime times f2 equals 0. In other words, c1 prime e to the 3x plus c2 prime of x e to the minus 2x equals 0. The second equation is going to be c1 prime f1 prime plus c2 prime f2 prime equals g of x, which in this case is sine of 2x. F1 prime, the derivative of e to the 3x, is 3e to the 3x. F2 prime, the derivative of e to the minus 2x, is minus 2e to the minus 2x. And so we get these two equations to solve. You probably know several ways of solving two equations and two unknowns. One way to do it is to use Cramer's rule. We're going to solve for C1 by looking at the determinant of one matrix divided by the determinant of another matrix. The denominator matrix are just the coefficients of C1 prime and C2 prime that occur on the left-hand side of this equation. And so e to the 3x is here, e to the minus 2x is here, 3e to the 3x is here, minus 2e to the minus 2x is here, multiplied by c2 of x. The numerator, if we're solving for this first quantity, c1 prime, we replace the first column of the denominator matrix with what we have on the right-hand side here, 0 and sine of 2x. Similarly, for c2 prime of x, we have the same denominator, but we replace the second column with 0 sine 2x in the numerator. And so then we can multiply these out by hand if we want to. This determinant up here is 0 times this minus e to the minus x times this over the denominator e to the 3x minus 2e to the minus 2x minus e to the minus 2x times 3e to the 3x. Basically, for a 2 by 2 matrix, the determinant is the product of the elements on the main diagonal minus the product of the elements on the secondary diagonal. So we can calculate these two pretty easily. So let's look at the calculation of the solution. Some of these calculations are shortened by use of SageMath, but we will see on the next transparency how we can evaluate integrals like this using integration by parts twice. So we saw that c1 prime of x is the determinant of this matrix over the determinant of this matrix. And remember, for a 2 by 2 matrix, its determinant is the product of the main diagonal elements minus the product of the secondary diagonal elements. So in this numerator, for instance, this determinant is 0 times this minus e to the minus 2x times sine of 2x. So this simplifies to minus e to the minus 2x sine 2x. Down here, the product of the main diagonal terms is minus 2e to the x. Then we subtract off the product of the secondary diagonal elements, which is 3e to the x. And those result in a denominator of minus 5e to the x, which we can simplify a little bit to get this. So c1 of x is c1 prime integrated. So we just integrate this with respect to x, and what we will get is minus 1 over 65 times 2 cosine 2x plus 3 sine 2x, all of this times e to the minus 3x. Similarly, we had c2 prime of x, when evaluated, is minus 1/5 e to the 2x sine 2x, and integrating this c2 prime, we get that c2 is the integral of this, which simplifies to 1/20th cosine 2x minus sine 2x times e to the 2x. So y sub p of x then is, by our method, variation by parameters, c1 of x times e to the 3x plus c2 of x times e to the minus 2x. Remember that e to the 3x and e to the minus 2x were solutions to the corresponding homogeneous problem. We know what c1 and c2 are. We just calculated them up here. Substitute them in, simplify, and we find that y sub p is 1 over 52 cosine 2x minus 5 over 52 sine 2x. So the general solution to our ordinary differential equation, our general solution y, is the particular solution plus the complementary function, the solution to the corresponding homogeneous equation. So we get y sub p, which is these two terms, and then the complementary function is an arbitrary constant times e to the 3x plus an arbitrary constant times e to the minus 2x. Here's how we can use SageMath to do the first part of that calculation. We could define A to be the following matrix, with the first row being 0 and e to the minus 2x, the second row being sine of 2x and minus 2e to the minus 2x. Then we can print out A. When we execute this command by hitting Shift-Enter, here is A. We can define B similarly to be this matrix here. These are the numerator and denominators of the matrix of the two matrices used in the calculation of C1 prime. So we'll then say that C1 prime is the determinant of A divided by the determinant of B, and let's print out what C1 prime is, and we get this. We notice that we have 1/5 times an exponential times a sine here, and we're going to have to integrate C1 prime with respect to x to get C1. So we can do that here. C1 equals the integral of C1 prime of x with respect to x, and then let's print out what C1 is. And it turns out that C1 is minus 1/65 times the following stuff. 2 times cosine 2x plus 3 times sine 2x, all that stuff, and then a second factor, times e to the minus 3x. Let's see how we can evaluate the integral of e to the ax sine of bx dx using integration by parts. Remember that the formula for integration by parts is the integral of u times dv equals u times v minus the integral of v du. So when we look at this, we need to decide what is going to be u and what's going to be dv. One obvious choice is to try letting u be e to the ax and let dv be sine of bx dx. So let's let u equal e to the ax, dv equals sine of bx dx. By differentiating this top equation, we find that du is ae to the ax dx, and by integrating this equation on both sides, we get that v is the integral of sine of bx dx, and that is equal to minus 1 over b cosine of bx. Okay? So the integral of dv is v. The integral of sine bx dx is minus 1 over b cosine bx plus an arbitrary constant, but in integration by parts, those arbitrary constants are superfluous. If you put them in, you'll find that you don't need them in the end. Okay, so then this integral is u times v minus the integral of v du. And notice there's a minus sign here in v. So minus a minus gives us a plus here. And then v du is this stuff right here. Now, we need to evaluate this integral. And if you look at it, it does not look any simpler than the integral we started with. Here we have an exponential times a sine. Here we have an exponential times a cosine. But bear with me, we will make it through this. So we're going to use integration by parts on this also. We're going to let u be e to the ax, and we're going to let dv be cosine of bx dx. These factors 1 over b and a can be pulled outside the integral as a factor of a over b. So letting u be e to the ax, then du once again is a e to the ax dx. And if we let dv be cosine bx dx, then by integrating this, v is 1 over b sine of bx. So what we have here then for this integral, after taking those constant factors out front, here's u times v minus the integral of v du. Okay, so then what happens? Let's see if we can simplify this a little bit. We have this term just copied down here. A over b times this term, we can simplify that a little bit because a over b times 1 over b is a over b squared. And then we have e to the ax sine bx. And then on this integral over here, we have an a that we can pull out front divided by b that we can pull out front, also multiplied times a over b here. And so all together that gives us minus a squared over b squared as a factor times the integral of sine bx e to the ax dx. And now we have something interesting happening. Here we have the integral of that sine times that exponential. Here we have the same integral of that sine times that exponential, but it has a different factor in front here. We can think of this integral as being the unknown quantity and solve for it. So let's add a squared over b squared times this integral to both sides of the equation. If I add a squared over b squared times this integral to the left-hand side, that's going to be 1 plus a squared over b squared times that integral. And then we have two more terms that we'll just leave as they were. Okay, So now we're trying to solve for this integral. So let's multiply by the inverse of 1 plus a squared over b squared. First of all, let's combine these two terms into one fraction with a common denominator of b squared. This simplifies to b squared plus a squared over b squared, okay? Which I could also think of as a squared plus b squared over b squared, just changing the order of the two terms in the numerator. So then, dividing by this factor, dividing both sides of this equation by this factor, on the left we get the integral that we're interested in, and on the other side we get that e to the ax times the inverse of this, which is b squared divided by a squared plus b squared, and then we have minus 1 over b cosine bx, which is right here, plus a over b squared sine bx here. Remember that e to the ax was factored out of here out front. Okay, so now if you look at this, it simplifies even further. This right-hand side, we have the factor of e to the ax, which is right here, okay? And now, here we have minus 1 over b. We can multiply it by this fraction, and we have a factor of b in both numerator and denominator. So that simplifies to minus b over a squared plus b squared times the cosine of bx. Okay, then the next term has a plus sign, and now a over b squared times this is what? You have a factor of b squared in both numerator and denominator. So that's going to simplify to a over this denominator, a squared plus b squared, times the sine of bx. And so this is what this integral is equal to. This exponential times, and if you wanted to, we could write a over a squared plus b squared sine bx minus b over a squared b squared cosine bx. And if you look at what we did in the last slide, you'll notice that we used this formula twice for integrating things that were an exponential times a sine. It's much easier to type it into SageMath and the answer pops up, but it's also very good to know how to do this by hand. So now let's move on to a slightly more complicated problem, an initial value problem. The differential equation, second derivative of y minus the first derivative of y minus 6 times y equals e to the minus x squared. Initial conditions, y of 1 is minus 1, y prime of 1 is equal to 2. So we want to solve this initial value problem. First of all, the left-hand side of this differential equation is identical to what we had in the previous example. And so if we look at this stuff equals 0, the corresponding homogeneous equation, the complementary function is c1 e to the 3x plus c2 e to the minus 2x, just as it was before. So in variation of parameters, we're going to look for a solution y sub p, a particular solution, is c1 of x times e to the 3x, c2 of x times e to the minus 2x. So we want c1 prime and c2 prime to satisfy the following two equations. c1 prime of x e to the 3x plus c2 prime of x e to the minus 2x equals 0. The e to the 3x and e to the minus 2x were these linearly independent solutions to the homogeneous problem. And then the second equation, c1 prime of x times the derivative of this, 3e to the 3x, plus c2 prime of x times the derivative of this, which is minus 2e to the minus 2x, equals the non-homogeneous term e to the minus x squared. Okay, we can solve these as simultaneous equations in two unknowns, C1 prime and C2 prime. I'll let you do that. That's basically junior high school or maybe high school algebra. When you solve those algebraically, you find that C1 prime of x is 1/5 e to the minus x squared minus 3x, and C2 prime of x turns out to be minus 1/5 e to the minus x squared plus 2x. So then we can write down what the particular solution is. It has to be C1 of x times e to the 3x plus C2 of x times e to the minus 2x. Now, what is C1? Well, C1 prime is this stuff, so C1 is going to be the integral of this stuff. And I'm going to write that as a definite integral, the integral from 1 to x, 1/5 e to the minus t squared minus 3t dt. Notice that I was basically integrating c prime of t here, going from 1 to x. And then it's multiplied by e to the 3x, which is right here. Now c2 of x is the integral of c2 prime, and so I'll write that as the integral from 1 to x minus 1/5 e to the minus t squared plus 2t, notice here we have x squared plus 2x, dt. And then it's multiplied by e to the minus 2x, which is what we have here. So the general solution then is what? Well, it's c1 of x e to the 3x plus c2 of x e to the minus 2x plus the solution to the corresponding homogeneous problem, the complementary function in other words. And that's just some constant times e to the 3x plus another arbitrary constant times e to the minus 2x. So we found the general solution, y of x equals the integral from 1 to x of this stuff dt times e to the 3x plus the integral from 1 to x of this stuff dt times e to the minus 2x plus c1 e to the 3x plus c2 e to the minus 2x. These first two terms give us a particular solution to the non-homogeneous equation, and to that we're adding the general solution to the corresponding homogeneous ODE. Now, we're not through. This is the solution to the ordinary differential equation. We need to satisfy two initial conditions. We, remember, are looking at an initial value problem. So we need to specify that y of 1 is minus 1, y prime of 1 is equal to 2. Those were our initial conditions. So coming up here, let's look at y of 1 first. The integral from 1 to 1, letting x be 1 in this case, the integral from 1 to 1 of anything is 0. 0 times 3x is 0. Maybe I should have said 0 times 3 e to the 3 times 1. For the same reason, the second term is also an integral from 1 to 1 of some stuff times some stuff. It's also 0. And so all we're left with is c1 e to the 3 times 1 plus c2 e to the minus 2 times 1, which is c1 e cubed plus c2 e to the minus 2. So that's y of 1, and it has to equal minus 1. That gives us a condition on these constants c1 and c2. Now, to find y prime of 1 and set it equal to something, we need to first differentiate this equation up here and figure out what y prime of x is. Well, if we look at this first integral, we're integrating from 1 to x, this function of t dt. If we differentiate this with respect to x, we're just going to get this function of x instead of t. And so the derivative of this integral is 1/5 e to the minus x squared minus 3x. And then that's multiplied by e to the 3x. Okay? And then we have to continue using the product rule. So far we took the derivative of the first factor times the second. Now we'll take the first factor times the derivative of the second factor. And so that's going to be that integral, and then the derivative of e to the 3x is 3e to the 3x. Okay? So now let's move on to differentiate this next term with respect to x. We'll have the derivative of this integral, which is just 1/2 e to the minus x squared plus 2x times this factor, e to the minus 2x, plus this factor, which is that integral, times the derivative of e to the minus 2x, which is minus 2e to the minus 2x. If we differentiate c1e to the 3x with respect to x, we get, I guess we already saw it down here, 3c1e to the 3x. And if we differentiate this term with respect to x, we get minus 2c2, makes you think of square dancing, e to the minus 2x. So now let's just evaluate this y prime of x at x equals 1. And so we get 1/5 e to the minus 1 squared minus 3 times 1, e to the 3 times 1, plus this integral times something which is 0, minus, and then 1/5 e to the minus 1 squared plus 2 times 1, times e to the minus 2, plus this integral times this, which is 0 times something, that's another 0, and then letting x be 1 in these two, 3c1 e cubed minus 2c2 e to the minus 2. And remember, the initial condition was y prime of 1 equals 2. So we found that the initial conditions are c1e cubed plus c2e to the minus 2 equals minus 1. And from up here, 1/5 e to the minus 1 minus 1/5 e to the minus 1 plus 3c1e cubed minus 2c2 e to the minus 2 equals 2. Notice where we got these minus 1's from. The exponent right here is minus 1 minus 3, and then the exponent here is 3. Minus 1 minus 3 plus 3 is minus 1. Over here we had minus 1 plus 2 minus 2 for the exponent when we take this product of exponentials, and that's also an exponent of minus 1. Interestingly, these two terms add up to 0, and we'll note that on the next slide. So the initial conditions gave us two equations involving c1 and c2. c1 e cubed plus c2 e to the minus 2 equals minus 1. 3c1 e cubed minus 2c2 e to the minus 2 equals 2. Let's eliminate c1 from these two equations. Multiply this first equation by 3. 3c1 e cubed plus 3c2 e to the minus 2 equals minus 3. And then subtract. And what you'll get, these will subtract to give 0. 3c2 minus 2c2, I should have said 3c2 minus a minus 2c2 adds up to 5c2 multiplied by e to the minus 2, and minus 3 minus 2 is minus 5. Divide both sides of this equation by 5, and we get c2 is minus e to the minus 2 power. Now substitute that into the first equation to solve for C1. So we get C1e cubed minus e to the minus 2 times, should have said minus e squared times e to the minus 2 for this. That has to equal minus 1. E to the second times e to the minus 2 is just 1. So we have this term minus 1 equals minus 1. And so C1 then has to equal 0. So we've now found out what C1 and C2 have to be, and we can plug them into what we found earlier as our general solution to the ordinary differential equation. Put a 0 in for C1, put a minus e squared in for C2. And so y then is this integral times e to the 3x plus this integral times e to the minus 2x plus this term, which turned into minus e squared e to the minus 2. This product of exponentials can be combined into one term, e raised to the 2 minus 2x power. So let's look at the solution that we got to this last problem. We're going to, in cell 1, produce that solution. Y of x is 1/5 the integral of e to the minus t squared minus 3 times t, integrated t going from 1 to x, and that integral is multiplied by e to the 3x, minus 1/5 the integral of e to the minus t squared plus 2 times t, integrated where t goes from 1 to x. That integral is multiplied by e to the minus 2x. And the last term is e minus e raised to the 2 minus 2x. Now, we're going to declare t to be a variable before we do this, since we're using t, and we'll assume that x is greater than 0. And so we'll define y of x this way, and then show what y of x is. Now you might think we'll see integrals going from 1 to x, but what's going to happen is the following. There's a built-in function in SageMath, and it's a standard special function, I guess, the error function of x, and it's defined to be 2 over the square root of pi, the integral from 0 to x e to the minus t squared dt. So what's going to happen is SageMath will write y of x using this error function. So I'm going to come down here and hit Shift Enter on this first cell, and we will wait for a few seconds for the answer to appear. And here it is. That should be equivalent to our formula up here, but it's written in terms of this error function instead. Let's plot y of x, x going from 0 to 2, and the graph of this function looks about like this, and we notice that y of 1 is minus 1 apparently, and if we look here, the slope looks like it's about 2. As we go over 1/2 in this direction, in the x direction, we're going up 1 in the y direction. So the slope looks like it's about 2. So let's see how well this function y of x does in satisfying the differential equation. So let's show the following. The second derivative of y with respect to x minus the first derivative of y with respect to x minus 6 times y of x minus e to the minus x squared. Okay. For this particular function y, this should be pretty close to 0. In fact, it should be the 0 function. We're showing what this function is, this expression is. Let's see if we get 0. We don't. That doesn't look like 0 to me. If you simplify this, perhaps it's 0, but I'm not sure. Okay, let's try simplifying this answer. So I'll have a dot simplify on this, and it basically gives me the same thing again. Can't tell how big this is. So let's now go numeric. Let's plot the second derivative of y with respect to x minus the first derivative of y with respect to x minus 6 times y minus e to the minus x squared. And let's plot it for x going from 0 to 2. That expression should equal 0 if our calculation is right. So let's see if we get a graph that is 0 everywhere. So here's the graph that we got. That doesn't look like 0, but let's look at it a little bit more carefully. On the vertical axis, we have the graph going from a little bit past minus 3 times 10 to the minus 16 up to 3 times 10 to the minus 16. If you think about it for a minute, 10 to the minus 16 is an extremely small number. It's very close to 0. And so what we have here is this difference of our differential expression and e to the minus x squared being very, very close to 0. But why are we getting a graph that looks like this? My guess is it's probably due to rounding error. Remember that the word size on a computer is finite. I'm not sure if in this calculation SageMath is using 64 bits or if it's using 32 bits. But in any case, it has to approximate things with a finite number of bits, and that causes, in many cases, round-off error to occur. So I'm pretty sure that these very small numbers that we see plotted here are due to round-off error, and this expression probably really does have the exact value 0. Maybe we should look at this for a while and see if we can show that this big expression is 0. But I don't think it's worthwhile in this case. Let's check a couple things. Our solution y of x at x equals 1 should be minus 1. So let's evaluate y of 1 and see what we get. Minus 1. How about the derivative of y with respect to x? Let's let yx equal the derivative of y with respect to x, and then let's evaluate yx of 1. What is the derivative of y evaluated at 1? That should be equal to 2. So let's see what happens here. And we get 2. So this function y of x that we found seems to satisfy our differential equation and the initial conditions. Let's see how we can let Sage do all the computations for us to find the solution to the initial value problem plus plot that solution. It only takes a couple of cells to do. In the first cell, we declare y to be a function of x, and then I'll define another function y Sage, and it's going to be the solution to the differential equation. So I have y Sage equals dsolve, and then in parentheses, the second derivative of y with respect to x minus the derivative of y with respect to x minus 6 times y minus e raised to the minus x squared power, and remember this equals 0. Solve it for y, and for the initial conditions, y of 1 is minus 1 and y prime of 1 is equal to 2. We'll show what y Sage looks like the solution that SageMath computed. Let's do that first. So I'll just come into this cell and type Shift Enter. It'll take a second or two or three or four. So that's what SageMath declares is the solution. And now let's plot y_sage of x, x going from 0 to 2. And so I'll do a Shift Enter on that cell. And here we get the solution to the differential equation computed by y_sage and plotted. As we can see for this graph, y_sage of 1 is -1, it seems, and once again the slope seems to be about 2. And if you compare this graph to the graph of the function that we computed earlier following variation of parameters, you'll see that they do appear identical. So what did we accomplish in this lesson? We saw how to use variation of parameters to solve non-homogeneous second-order ordinary differential equations, and we showed also why this method worked. Along the way, we saw that the ordinary differential equation in this case, for this method, did not necessarily have to be a constant coefficient ordinary differential equation. We only looked at second-order differential equations, but I should note that this method can be extended to higher-order equations, third order, fourth order, and so forth. We solved a couple problems using this method. I think one was just an ordinary differential equation, and the other was an initial value problem. We used SageMath for computations in order to solve and plot the solutions, and we used SageMath DE_solve function to solve and graph the solution to our initial value problem. DE_solve allowed us to skip most of the hand calculations and just ask SageMath to solve the initial value problem for us. I hope you enjoyed this lecture, and I hope you come back for more. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.